Hello everyone, October the 3rd. Alright, let's get this done for today. We don't need this one. Alright, path sum. Given root of the parent tree and integer target sum, return true if a tree has a root to it. Can we do this? Yeah, I feel like we've done this very recently. Doesn't matter. Doesn't really matter when we do this. We just need to do it today. Maybe we can directly do this. Yeah. Oh, we need the current sum. Need a current sum. Right. So if not node dot left and not node dot right. No, let's say current sum plus equal. Ooh, hold up. We will not get into, yeah, so we're saying node is always, yeah, could be an empty node, right? Could be an empty node. So we should say if not node, shall return false, no matter what. And then current sum plus equal to, not current sum plus equal to. Just if this, and then we shall return current sum plus node.val. Yeah, okay, plus equal to. And then we say current sum equal to target sum, right? And then if node.left, then we say DFS node.left. Oh, and then we can just return DFS node.left current sum or DFS node.right. So that shall do, right? DFS root, and let's start with 0. So ideally, you shouldn't get into the situation where we will go for a empty node, but need to be cautious. No, it's 2021. It's more than a year ago. No, it's about a year ago. Yeah, nothing too hard. I think it's something similar recently we done. Don't remember specifically. 112. Okay, so that's that. So we've done this. Now let's do this complete binary tree inserter. A complete binary tree is a binary tree in which every level except possibly the last is completely filled. Okay. Design already insert a new node to a complete binary tree, keeping it complete after the insertion. Initialized with a root. Inserts a tree node into the tree with value, so that the tree remains complete, and returns the value to the parent. Returns a root node. Okay. So 1, 2, 1, 2, 3, 1, 2, 3, 4. So this is still a complete. So complete. Yeah, I think complete binary tree is every row, every level is filled except for the last row, which should be filled from the left. Okay, so basically, every time you add, how do you add? How do you add it faster? I mean, we could have just kept, let's say we kept the current row. Can we do that? We kept the current row. Oh, can we add directly? Yeah, for each one we ask, do we have a left? Do we have a right? If we do, we go this. Then what if it's here? So, and also we only have 1000. Yeah, definitely. We keep the row. We keep the row. So we have the initialization will give you the, wait, what does initialization do? 1, 2. Oh, initialize with, I think I can, wait, initialize the root. What? How do you get both? What are you supposed to initialize with? Oh, my bad. Initializes nothing, and then this is pointing to insert. No, that's initialize. Initialize. Wait, can we like initialize 3 things? I guess we can. So we initialize with a list. That's not a tree node. How is this a tree node? Yo, this is confusing. This is very confusing. Oh, I think this probably is a left. Yeah, I think that's probably a left, because, you know what, I don't know. But this just give you a root. And you're supposed to only have the root, right? Insert, get root. And what does insert return? Insert return the parent. What the hell is this? What? Optional. It's a tree node. How is this a tree node? You know what? I need to I need to poke this. Let's say we do, I don't know, does this one work? We pass 1. What does that mean? Nah, pass. Yeah, I think what I don't know is, I don't know what this means. Okay, so expected, no, and then 1. So that's when we insert. So 1, 3. Okay. Okay, so what if I get 1, 2, 3, 4, 5, 6, 7, 8, 9? What does that mean? Is the previous just become? Oh, it's already given to you. Okay, I know what it means. I know what it means. It's a tree. They give you a tree, the root to a tree. It's already done. All right. So what we need to do is given the tree, and we set up a queue, and all we need to know is the current row. We get the current row, so we get the parent. Ooh, get the parent. Damn. It's just, it's not as easy, huh? So we have the first level, right? And then we go to the next level, and then we go to whichever level is. I think I need a data structure for this, which is just a list, right? A list, and then we'll record each row, right? So the new one comes in, we can go to the previous row and find out where we should do, and then we insert and we put in the current row. And then when this row is exhausted, we swap. So previous row and a current row, right? Previous row and a current row. And number of nodes will be 1, so at least we'll have 1, right? At least we'll have 1. And only insert and get root. So get root will always return the same thing, right? Yeah, the get root. Oh, the get root, they will try to do this. Okay, so I have an idea. I think it will work because there's only very few nodes, so this will work. Of course, there's no test case for me. All right. So all we're gonna do is root. So we'll say self.root equals root, right? And we're gonna do a little bit self.preq, right, equals root, and self.currentQ equals, I don't know what. So while self.preq self.currentQ equals this. We don't need this. Just do this. For node in self.preq, if node.left self.currentQ.append node.left, if node.right self.else, if we have a node which doesn't, then we just break. Okay, and then once we're done, we say else, which means it doesn't break. We just handle everything and we don't break. Then we say self.preq equals self.currentQ. All right, and then we go do it again. And then if we break, and then we continue. If we break, then we break, which means we have gone through, we have get all we need. Yeah. So we handle this to get the 2 queues. How the end is going to be, well, if it's complete, right, which means I have everything, and if I have everything, I say self.q equals this, and then we go back up, and then we try, and then for node nothing, then we break out. So the current queue will be empty. Yeah, I think this is right. All right, so insert. But we need to know where, which the parent, right? The parent, can we deduce where the parents are? I think we can, based on how far this one goes, because it's always double, right? So if this is, if the length of the current queue is even, then it's just this one divided by 2. Then that will be the index. If it's odd, then will be this. Let me think. 4 divided by 2 is 2, so 0, 1, 2. right? If 5 divided by 2, it's 0, 1, 2. It's the same. So what we can do is, how do we know the length has been filled? Well, we do know when it's filled. What we say is, if this, and then, hold on, let me think again. So divided by 2 will point it to this, right? And if this divided by 2, then will be too much. Then we can swap. Okay. So we say index shall equal to len self dot current q divided by 2. We say if index is smaller than len self dot previous q, right? Then we say self dot previous q index left or right. We have to say if len self dot q. Oh, I can just do index quotient remaining div mod. Easier, right? Yeah. So if q is smaller, and we say if r, which is even, which is odd, then this dot, yeah, I don't like q, I like index. So it's odd, right? So the index is odd. Oh, index is odd. Hold a second. It's this. No, that's not index is odd. It's the r. It's the self dot length. The length is odd, right? The length is odd. So it's going to be index dot right equal to tree node val equals to val, right? Else it's even, then it should be self dot pre q index dot left equals tree node val equals val. And when we're done both, we shall say self dot current q dot append, holy crap, node, and then we will change this to node, and then we'll append the node, right? Which is just extended. Perfect. So that's that. All right. So what if it's else? Okay. Else, which means it's too much. So we're gonna swap, right? Which means we'll say self dot pre q shall equal to self dot current q, and self dot current q shall equal to, and then we say index. We can do this. We shall do this. If index is equal to len self dot pre q, then we swap them. This will be this, and then we say index equal to 0, right? And then we handle this, get a node. Index equal to, the r must be 0, right? R must be 0. So if r is 0, then we do the pre-q 0 to the left. That makes sense. All right, so we're gonna return. What do we return? Value of the parent of the inserted. So it shall be the value of the parent, which is self.preq index.val. Okay. Get root self.root. This is actually, get root is nothing. So we have one function, right? One function that's kind of a little bit tricky. Let's see. We'll see if this is right. That's a good test case. Actually, I like it, but I will use this. do this. I'll do this. And maybe I'll do one more. I'll do more insert. Four. Okay, we insert 4 more times. And then we can say 1, 2, 3, 4. They can't be the same value, right? There's nothing says they have to be different values. Okay, let's try this. I think we have some issue here. Oh no, we don't have issue. Why is it so slow? Okay. And we're always 1, so I think we are good to go. Yeah, we tested 2, a bunch, a 1. I want to add a bunch of stuff. Yeah, let's go for it. Oh yeah, wrong answer. Wait, hold up. I have this test case. Oh, we missed by 1. Dang. We got an error. Output, I have a null. What the heck? Alright, let's see. I have 1, 2, 3, 4, 5, 6. Okay. Yeah, let's focus on this one test case. The other test cases. So what I want is I need to know where things are. Okay. So for node in self.preq, print node.val. Is that sep? I don't know. I haven't used this for a long time. Or a separator. And insert. I forgot. I don't print separator. Too long time ago. Sep. Yeah, it is sep. So insert. I'll also do this. Okay, so now let's see what we're gonna print out. And kind of peek into our problem. What the heck? What is this? Huh? What is this? Is the separator not working? Sep equals. Print sep equals. Yeah. I have sep equals. I don't understand. I have sep equals. That is weird. But anyway, why are they all full? I don't know what happened. I guess this is easier. Invalid syntax, of course. I forgot the parentheses. 4, 4, 4, 4. That is weird. What? What the hell? Oh, God. Oh, man. You're dumb. Yeah. Typo. I copy and paste the line, that's why. Alright, let's bring these back. And how do these all correct? Huh? It's like completely wrong. How are all these become correct? Yeah, it's beyond me. I don't know. That's that. Yeah, I think this is the only thing. Got a bit typo here. Let's put it here. Keep 2 arrays that point to the current level of the tree and the previous level. Use the length of the current level to determine the next parent on the previous level. And don't forget to switch level when the current level is filled up. That's basically it. And check a deck. A deck. Current. Oh, yeah. We can do deck. Yes. Yeah, it's basically the same. This is a deck. This is a deck. A deck is just every time you use it, you just push it out. And then next one come in, you check this and you push in. Next one come in and you use what? To determine when it's done. Even or odd. If it's even, then we keep going. If it's odd, then we push. That's what I think. Or you can just keep track. Yeah, or you can just keep track. We're gonna append it. Oh, we can check if not left, then we add it. Nice, good solution. We never need to pop from the right. No, we never need to pop from the right. A single queue. We can use a single queue. How do you use a single queue? You just keep adding to the right. Yeah, you just never pop, but the thing can grow, right? The thing can grow. I don't even know what AVL tree is. Self-balancing tree. talking about premature optimization is the evil of all things. Deque is a queue. Okay, let's try the Deque solution. It's better than 2, I guess. But everything should be the same. I don't see this one to be any different. But it's good to practice Deque. Okay, using Deque. Then we should say self.q equals a Deque. So basically we're using Deque to do this. We have to put a root in it. So while self.q node equals self.q pop left. Do I have underscore? No, I think there's no underscore. And for now, I'm going to say self.q.append q.append else, and then break. Else continue, and then break. So we'll break out early. Wait, hold on. Are we keeping everything? No. We add this, so we pop it. Right, so we go to the next one. Add this, pop it. Go to the next one. Nothing to add. Oh, then we just break out. Alright, nothing to add. And if we added everything, then we keep going. Right, if we added everything, then we need to keep going. So yeah, this is right. Or if not left. Hold a second. I shouldn't pop on the left, right? Wait, hold on. Just not this thing. Dude, come on. Should be 0. If this, and then self, what can self.q dot pop left, so we know both fits. If this, then we just break. Yeah, so like the current node, it has left, so we push it in. If it doesn't have a right, then we just break. But we don't pop this one out. But if it has right, then we pop this. We can pop this and go for the next one. Okay. Now insert. Oh, then we don't need this. Wow, we don't have to do this. How do we insert? We have the parent shall be self.q 0, right? And then node shall be this. The parent, we have the node. And we say if parent dot left, right? If not, parent dot left equals node. I can say self.q.append. We're always going to have to append. So this will equal to self.q minus 1. Understood. Right? Elif else. Elif parent.right, not parent.right. They cannot both be, so actually we can just say else parent.right equals self.q. But if it's right, self.q.pop left. We have to pop it. Right? And then we're gonna return parent. So much shorter, huh? .val. Okay. Let's try this. Use the official solution. Use Q. Use a Deque as in the official solution. Oh shoot, it's node number 2. Yep. Nah, Deque is better for this. Better for the job. Oh, a lot faster. A lot faster. But a lot faster. Okay, that will be it for today. Pretty good. Alright, I will pick one for tomorrow. And I will see you guys tomorrow. Adios.